Hello, we are going to be starting chapter number 2, atoms, molecules, and the mole concept, with the unit 1. And so here is the unit 1, and the contents are, we're going to study atomic structure, atomic number, atomic mass, describe electrons, protons, neutrons, the general structure of the atom, define terms, atomic number, mass number, and define isotopes, and then calculate the atomic weight or mass of the element that is present. Basically, the identification of subatomic particles present in an atom was based on experiments that involved the detection of the charged particles, positive or negatively charged subatomic particles, and the uncharged particle that was present. The atom, this electric nature of the atom was very important in discovering its subatomic structure. And we use the law of electrostatic attraction, which says that like charges repel and unlike charges, opposite charges attract. Now, the atomic composition of any given atom consists of a positive electric charge, which is called as the proton, and it has a mass of 1.672622 times 10 raised to minus 24. And we, in terms of the atomic mass unit, it's about 1.007 units. Now that is there. The mass of the electron is, the electron relative mass is 0.005. It's negatively charged particle. The neutrons has no charge on it, but its mass, relative mass, is 1.009 units. And this is easier to remember than the masses in grams because they are extremely small. And at this point in time, if you know the relative masses, then it is equal, and we can apply it for calculation purposes. The atom by itself is a neutral particle. And therefore, it consists of equal number of protons and electrons that are there. The mass of the atomic mass of an atom is the sum of the proton and the neutron, because the mass of the electron is very, very small and can almost be neglected when compared to the mass of the proton. The atom generally consists mostly of empty space. The protons and neutrons are found in the nucleus. The number of electrons is equal to the number of protons. Electrons occupy the space around the nucleus, and the nucleus is very, very small. 1 teaspoon of water has 3 times as many atoms as the Atlantic Ocean has teaspoons of water. So you can see how much small they are. Now, whenever we write how do we represent an atom? If you look at the periodic table, all atoms of the same element have the same number of protons in the nucleus. Now, this is to be read very, very carefully because it says all atoms of the same element. So different atoms have different number of protons in the nucleus. And the Z is called as the atomic number, and it represents the position of the atom on the periodic table. Now, for example, on top of on any periodic table, you will see the symbol for an element in the middle. On top of it, you have a whole number, and at the bottom of it, you will have a number that has got a fraction on it. The top number, which is a whole number, is called as the atomic number, and it is represented by the letter Z, and it corresponds to the number of protons that are present in the atom. This means that Z also represents the number of electrons. The number At the bottom of the symbol represents the atomic mass. And since it is fractional, we will have to see how we get this fractional part of the element mass that is there. So now, in general, we can write any element by using the notation shown below, where A is the mass number. Remember, Z is the atomic number and it represents the number of protons. A is the mass number and the mass number includes the number of protons and the number of neutrons. Sometimes it is possible to give the mass number of an element, and then you can look at the number of protons by looking at the periodic table. Now, mass number A, a C12 carbon, as you can see, I'm not put the atomic number. The C12 carbon has 6 protons and 6 neutrons. The mass number A is 6. The mass number A is 12, and it has 6 protons and 6 neutrons. Carbon 12 has a mass of exactly 12 units. Carbon 13, on the other hand, has 6 protons and 7 neutrons. And so when the same atom has different number of neutrons, then we call it as isotopes, because there is no differentiation of position. The number of protons is the same in carbon 12 and carbon 13. And so on the periodic table, they will appear in the same spot. So how to identify an isotope? The isotope has the same number of protons but different number of neutrons. For a given element X, an isotope is written by the atomic number Z, the number of protons in the nucleus, the mass number A, total number of protons or neutrons in the nucleus. One proton or one neutron has a mass of 1 atomic unit, or a Dalton, or we just say a U, represented by the letter U. Now, the relative atomic mass. What do we understand by the term relative atomic mass? Basically, it means we are going to compare. Relative means we compare one atom with a standard atom that is there. And generally speaking, the standard atom used is one atom of carbon 12, whose mass is 1.99266 times 10 to the power negative 23. And when we compare it, then we can write the mass is equal to the mass of carbon atom divided by 12, which gives you 1.66054 times 10 raised to minus 24 gram, or 1.66054 times 10 raised to minus 27 of a kilogram. Calculation of relative atomic mass using the standard carbon-12 Z6. The atomic mass of one element of an element is related to one atom of another element. An oxygen atom has approximately 16 times more mass than an atom of hydrogen. The standard is based upon the carbon-12 isotope, which has a mass of 1.99265 times e to the negative 23 grams. The atomic mass of carbon is defined as exactly 12 units. It is used as a comparison for masses of atoms. Therefore, 1 unit divided by the mass of one carbon atom divided by 12 gives you 1.66054 times e to the power negative 24. That's how the math is calculated. But you still have to remember the unit, the one atomic mass unit. Remember, the one atomic mass unit depends upon the standard that is used. And the standard used is carbon 12, which has exactly 12 unit mass and 6 protons. Now, if you change the standard, then naturally the atomic mass and the relative masses will change. So now we show a representation of how for fluorine element 19, and has mass number 19, which represents the number of protons and neutrons, and the atomic number below is 9. So the existence of isotopes means that all atoms of an element are not exactly the same. So all atoms of the same element have the same number of protons in the nucleus. Atoms of the same element that have different number of neutrons in the nucleus. And therefore, for any given element, this is the general way, expression, how we write. And in order to remember it very simply, just write the number. If you ask the question, what are the list the alphabets, then we say that in the English language, the alphabets are from A to Z. So A is the mass number, Z is the atomic number. Mass number is A, that is, we write on the left-hand top corner as an superscript, and Z as the atomic number is written as the subscript. In that way, you can easily remember it. Now, how do we determine the relative abundance of any particular element? Atoms are isotopes of a given atom. What we do is this is a typical experiment to detect the isotopes in a given sample. So we pass the gas through a repeller, then it passes through an electron gun. And as it passes through the electron gun, it passes through the accelerating plates. As a result, we can know that heavier particles will move slowly and lighter particles will move faster. Once they are separated in that way, we apply a magnetic field, and the heavier ions are deflected too little and the lighter ones too large, and you can see how the separation occurs. Once it goes to the analyzer, to the vacuum pump, this whole tube is vacuumed off or emptied of any air or gas, and then the sample is placed inside, and then of course the detector screen will locate what type of masses are there, and the picture that appears from the detector screen is called as the mass spectrum, and it is represented on a graph sheet where relative abundance is on the y-axis and the isotopes are given on the x-axis. And with that, we can find out the abundance and the nature of that particular element that is there and how many isotopes are there. Because depending upon the isotopes, you would get a picture or a screenshot like this, where abundance and mass is given and the relative abundance of different isotopes are given. The instrument that we use is called as the mass spectrometer, and it gives information on the mass and the relative abundance of each isotope. The analysis of hydrogen shows that there are 3 isotopes, and they are like the actual hydrogen atom, which consists of 1 electron, 1 proton, but no neutrons. The second one is called as deuterium, and it has 1 proton, 1 electron, and 1 neutron. And the tritium, which is found on the surface of the sun, has 1 proton, neutron, 2 neutrons. And you can see also how if you take a glass of water with different forms of the proton, hydrogen combining with water. Oxygen gives you water, H2O. Deuterium combining with water, oxygen gives you a liquid that is 1.11 grams per centimeter cube. So that water by itself at 25 degrees Celsius, 4 degrees Celsius is 0.9998 grams per centimeter cube. Now, how do we calculate the percentage of abundance? This is a very simple concept that is there. Now, percentage abundance, that means you have large number of different types of atoms of the same element. But they differ in mass because of the difference in the number of neutrons. Therefore, we can calculate the abundance of each element's isotope first as a fraction, the number of atoms of a given isotope divided by the total number of atoms of all the isotopes of that element. First, and that is called as the fractional abundance. Now, if you multiply the fractional abundance by 100, then you will get the percentage abundance. So this is very useful to remember. First, calculate the fractional abundance, number of atoms of a given isotope divided by the total number of atoms of all the isotopes that are present in the element, and then multiplied by 100. The atomic masses on the periodic table are the sum of the weighted averages of all the masses of all the elements' individual isotope masses and its abundance. So we say we have the basic mathematical expression is that abundance of isotope 1 you divide by, because they are giving percentage abundance of isotope 1 divided by 100. As a result, the 100 will cancel off, and therefore you will get a fractional abundance times the mass of the isotope 1, fractional abundance of isotope 2 times the mass of its isotope 2, and so on. So basically, you just have to add it up. And a typical example is given to you so that you understand how to calculate it. So here it is. The mass of an isotope is a weighted average, and it is determined by the following mathematical expression. So the average atomic mass is equal to the mass of the isotope 1 times the fractional abundance of 1 plus the mass of isotope 2 times the fractional abundance of isotope 2. And it continues this way. But remember that you cannot add the mass of isotope 1 and the mass of isotope 2 and then add the abundance of 1 and 2 and then get the average. No, you have to do it individually for each isotope that is there. And what do? Mass of isotope times fractional abundance for that isotope. And the problem is shown over here, wherein we try to detect the percentage, the average isotopic mass of chlorine. The natural occurring chlorine is 75.53% of chlorine 35. And the atomic number of chlorine is 70. Which has an atomic mass of 34.96885 units. And the mass of isotope 37 is 36.96590, and its percentage abundance is 24.47. Calculate the average atomic mass, that is the atomic weight of chlorine. So using the expression above, we multiply the mass of chlorine 35. So 35.96885 times divide 75.53 by 100. In 100, you have 2 zeros. So shift the decimal places 2 places to the left. And so you mass 34.96885 divided by 0. Not divided, sorry. Start all over. 94.96885 multiplied by 0.7553 plus mass of 37, which is 36.96590 times the fractional abundance of Cl37. The percentage of Cl37 is 24.47. If you divide it by 100, it becomes 0.2447. And therefore, we get the mass of chlorine 35 as 34.96885 times 0.7553 plus 36.96590 times 0.2447. And if you add this up, then you get the mass of chlorine as 35.45 for 4 to 4 significant figures. Now you have the study. After this, all the items are study concept. And with that, I'm going to stop the calculation, the slide presentation, and open up the next one, Unit 2.